These are notes for AP Calculus on the topic of graphing and transformations. So let's first take a look at some of the 8 basic functions. Basically, you should know what their graphs look like. To review those, make sure you do remember. So the first one is just f of x equals x, or y equals x. So this is, what are straight lines, or what do we call linear functions? So this is a linear function, and then underneath each one of these, we'll write down its domain and range. And then we'll look at the transformations that can be applied to these and see how that affects their domain and range. So, linear domain, remember, refers to all the possible x values. So we look from left to right here. Domain, you can see this arrow here goes all the way to negative infinity as we head to the right, all the way to positive infinity. So the domain would be from negative infinity to infinity, interval notation. And then the range, all the possible y values, so you go from bottom to top. This one heads down forever to negative infinity, and then it goes up forever, all the way to positive infinity. So the range would also be negative infinity to infinity on this one. So this is linear when you have a line, which makes it straight. Then we have f of x equals x squared. This is what's called a quadratic function. Or the shape of it is referred to as a parabola. And let's look at the domain and range on this one. Again, the domain is all the possible x values, so you look from left to right. And you can see it heads to the left forever, and then to the right forever, all connected, so the domain is from negative infinity to infinity. But the range on this one is a little bit different. The range, remember, refers to all the possible y values. So you go from bottom to top, but this one, notice there are no arrows pointing down. It doesn't go to negative infinity. So if we head up here, the lowest y value it reaches is 0 right there at the origin. And since that is a point, there is a point there, that would be included. So 0 with a bracket, comma, and then you can follow either one of these that go all the way to infinity, go up forever. The y value, so it would be 0 to infinity. All right, let's take a look at the next pair. So this is what's called a cubic function. Y equals x cubed, and it looks like this. So let's look at the domain and range of this one. So for the domain, we look at all the possible x values. So this keeps going left forever, so to negative infinity. And it's all connected, it keeps going to the right forever, so to positive infinity. And the range, all the possible y values. So from bottom to top, this heads down forever to negative infinity, and it goes up forever to positive infinity. Now let's take a look at the square root graph, y equals square root of x. And look at its domain and range. The domain on this one, as we look from left to right, this one doesn't go to the left forever. It doesn't head to negative infinity. First x value we hit right there is 0, and there's a point there, so that's included from 0. And then it goes right forever to positive infinity. And the range, all the possible y values, go from bottom to top. Again, there is no arrow that goes down forever, so it does not start at negative infinity. The first y value it hits is right there at 0. And there is a point there, so that would be included with a bracket. All the way, it keeps going up forever, although very slowly, so it goes up forever, so that's 2. Okay, let's go to the next pair. So this is an absolute value function, or I should say more specifically, it's a linear absolute value function. It's like a V here. See? And let's look at the domain and range here. So the domain heads left forever, so it starts at negative infinity. And it's all connected, it heads right forever, so to positive infinity. range, it doesn't head down forever to negative infinity. There's no arrow pointing down, but so its lowest y value is right there at 0. And there is a point there at 0 with a y value of 0, so 0 with a bracket. And then either one of these go up forever all the way to positive. Now let's look at the f of x equals 1 over x graph. Okay. And this one, you'll notice, has a vertical asymptote at x equals 0 right here. Draw that in there if you want. I'll just put some dotted line here. So we've got a vertical asymptote right there. And you also have a horizontal asymptote at y equals 0 right there. So let's look at the domain range of this one. The domain on this one, you can see this heads to negative infinity, to the left forever. But as we head this way, it doesn't head to the right forever, it heads all the way until 0. So it'd be from negative infinity to 0, since we have a vertical asymptote there. And then parentheses on 0, because it's not included. And that's union with the next one starts right after 0 here, with the parentheses, because 0 is not included, and it goes right forever all the way to infinity. And the range on this one, you can see it heads down forever with that arrow to negative infinity. But as you head up, notice it never touches the x-axis here, so y is never 0. You stop at 0 with the parentheses. And that takes you to right there. And union with this interval starts right above 0, so 0 with the parentheses, and it goes up forever all the way to infinity. And the final pair you should be familiar with are the exponential, and in this case this is the natural exponential. It's got a base of e. And the natural logarithm. Because this, remember, means the same as log base e of x. Where e, remember, is a constant approximately equal to 2.71. An irrational number like pi. Okay, so the other regular exponential logarithmic functions have similar shapes. They're just all slightly different in steepness depending on their base. In this case, it's e. So let's take a look at the domain range of each of these. The domain on the exponential graph, this goes left forever, negative infinity, and this goes right forever, instead of positive infinity. And in the range, it doesn't go down forever because there's this it does have a horizontal asymptote right there at 0. Because no matter what you put in for the exponent, e, some positive number, 2.71 to any exponent is always going to give you a positive number. So the range actually starts kind of at 0, but it never actually touches 0, even though it looks like it never quite gets to 0. So it'd be 0 with a parentheses. But it does go up forever from there, so all the way to infinity. And now let's take a look at the logarithmic graph. So in this one, you can see there's a vertical asymptote right here at x equals 0. Because remember, for the restriction on the domain of logarithms is what's inside the log has to be greater than 0, has to be positive. We can see that graphically. So the domain, it does not go left forever. It starts right here where it's positive, so that would be 0. Again, it never reaches 0 because of the vertical asymptote, 0 with the parentheses. But it keeps going right forever, so all the way to infinity. range, well, starts at, heads down to negative infinity, right there, and follow it up, and it keeps going up forever, so to positive. All right, before we move on to the next examples here, take a look at the domain and range of e to the x and the domain and range of natural log of x. Notice how those are reversed there. The domain of e to the x is the range of natural log of x, and the range of e to the x is the domain of natural log of x. And that's not a coincidence, that's because these are inverse functions. When they have the same base like this, they reverse each other. All right, now let's take a look at the different transformations you can apply to these family functions and really any function that you encounter here. So let's look at the horizontal shifts first. So C here represents some positive number. Okay? So if you have x minus C, I'll put a specific number in there. Say we add x minus 2 in for wherever there's an x. Now this is, the horizontal ones are the ones that are initially may seem counterintuitive because you think of negative, you're thinking left. That actually shifts it 2 units to the right if you had a minus 2. The reason, the way I remember this, why it's to the right, is when you plug in 2, minus 2 for x, minus 2, that would give you 0. Okay? So if you're plugging in 2, you're actually getting what it was for 0. Okay? So what it was for 0 is now over here at 2, hence it's shifting it 2 units to the right. In a similar way, if you have x plus some constant, let's say 2, we remember why this is shifting it to the left, and on counterintuitive not to the right, is because this means if you were to plug in negative 2 for x, you'd get f of 0, what it would be like for 0. So now normally what was at 0 right here is now going to be here at when you plug in negative 2. So that's why it shifts it to the left. All right, now the vertical shifts are a little easier to see why those would be. You have a number on the outside that's added or subtracted. If it's subtracted, you're just subtracting that value from the y-bias, so that's shifting it down, that many units. If it's added, then it's shifting it up. That means because you're just adding up to y-bias. And then the last ones, if you have a negative sign there, depends where the negative is. Remember, f of x is like y, so if you put the negative out in front of the function, that's a reflection about the x-axis. Because everything that was up here is positive would now be down here negative, reflective about the x-axis. But if a negative is in here, inside with the x, not on the outside, then it would be a reflection about the y-axis because now you had some x value over here, you plug in that negative x value. Over here, that negative sign is going to change it back to positive what it was over here, so it's going to reflect it about the y-axis. So let's see how we use these in conjunction with an actual specific problem. Okay. So this says, without the use of a calculator, graph the basic function and its transformations on the same set of axes. Okay, so we're going to graph all of them on that here, and find at least 3 points for each graph. Include the table of points you're using for your graph. Use different colors for each transformation. In the same color, state the domain and range of each graph. All right. So let's say we do the parent graph here is the 4 through x. So some of these will be the ones, those 8 we looked at, some of them may be different. In this case, we've got the 4th root of x. So let's just set up a little table here. We just need at least 3 points. So x and y, which in this case is f of x. Always, it says we just need at least 3 points. You can get more than that if you want to, but at least 3. So let's think about what would be easy to plug in for x here. It's a 4th root, so we can only, even root, we can only plug in numbers that are greater than or equal to 0. So let's start with 0. Well, the 4th root of 0 is just 0. So that's an easy point to start with. 0, 0. Graph there. What else do we know the 4th root of? Well, we know the 4th root, any root of 1 is just 1. The 4th root of 1 is 1, so it goes to the point 1, 1. And you can see with those 2 points, you don't really get a sense of what the graph looks like. It's not a straight line here. So that's why I need one more point. Another one we know the fourth root, without having to use our calculator here, is 16. 2 to the fourth is 16, so the fourth root of 16 gives you 2. So 16 will be over here at 2. And that's enough to graph it. So it kind of looks like the square root graph, except it doesn't increase as quickly as a square root graph, because the fourth root, which makes it even smaller than a square root. So again, we can't plug in negative numbers here, and this will never give us a negative number, so the graph curves up like this. Keeps on going up, just not very quickly. All right, now let's take a look at g of x. So let's say we use blue for this one. Oops. Set up a little table. Now, you could plug in numbers just like we did the original one, but there's a much, much easier way, and that's to use the transformations. Notice on this one, got a -3, now that's inside with the x, okay? Inside the fourth root. So that is not like, it's like this one, or it's inside with the x, not like it's on the outside. So that's remember a shift to the right. So in this case, that -3 is going to be shifting 3 units right. So all we have to do really is take the points we already found for f of x and use our transformation. That's the easiest way to graph what this would look like. So when you have 0, 0, we go 3 units to the right, that's going to increase the x coordinate by 3 on all these. So we'll have 3 is 0, 3 plus 0. 3 plus 1 is 4, so we'll have 4, 1. 3 plus 16 is 19, so we'll have 19, 2. So let's plot those points. 3, 0 right here. 4, 1 right here. And 19, 2. And I'll grab this one, different color. Keeps on going up, but just very slowly. You can see that shifted 3 units to the right. Let's try this one in green here, h of x. Oh, I guess we can be writing down the domain and range of each of these at the same time. So let's go ahead and do that. Actually, let's graph them all and then I will write the domain and range. That's probably easier. All right, so x and then h of x. Again, just go back to the original function and use the transformations. That's probably easier. This one actually has 2 different transformations. Notice. One, it has a +6 on the outside. Notice this is not on the inside like this one was. On the outside of the radical. So when it's on the outside, that's a shift up or down with plus. See, that's a shift up. Like that. So that's 6 units up. That's one of the transformations. But that's not the only one. Notice there's also a negative out in front of the fourth root. So that's going to be a reflection, and when it's out in front, like this, that's a reflection about the x-axis. That's an x-axis reflection. So it actually does not matter which one of these you do first, whichever one you think is going to be easier. Okay? So I'm going to reflect it about the x-axis first, right? And then shift it up 6. So, well, actually, yeah, it doesn't matter in the sense of what order you do it in terms of your reflection there. So notice what would first happen is the x would get, fourth root of x would first get reflected about the x-axis because multiplication happens first, and then you would add 6. So it is important here to do the reflection first. Okay, so let's first reflect it about the x-axis. So normally it would go up like this, like the red one. Reflecting about the x-axis would now head down like this about the x-axis, but then it shifted up 6. So let's take each of these points here. 0, 0, when you reflect it would still be at 0, 0, and then up 6. Be right there. So that would be the point 0, 6. The other ones are a little bit trickier. If you reflect them about the x-axis, this point 1, 1 would be down here at 1, -1. So reflect about it. and then shifted up 6, 1, 2, 3, 4, 5, 6 would be right there at 1, 5. And finally, our last point on the original is 16, 2. If that point gets reflected, and why did I graph that in the wrong place there? Sorry, I just realized I graphed that one in the wrong place. It doesn't change the shape too much, but the point I put right here, I don't know why I put 11 there. Must have thought that was 15. So, the point here really should have been right here at 16, 2. Okay, sorry about that. So 16, 2, that would be reflected down here, would be at 16, negative 2, when you reflect about that. And then adding 6 to that, when you add 6 to negative 2, you're up at 4. So 16, 4, right there. And then you can see the graph would look like this. Heading down forever, just very slowly. All right, now let's look at one last one. That's j of x. Let's see what color we can use here. Light blue. So for j of x, we set up a little table here. Let's try using those same 3 points. So this time we've got 2 things happening again. First, the x has a negative on the inside. That's this type of transformation. When x is on the inside. Okay. And then we have a minus 7 on the outside. That's 7 units down. So that negative over here, that's a reflection about the y-axis. And then 7 units down. Again, that happens first, and then you shift it down 7 units. Okay, so let's take our original points here. Start with 0, 0. Well, after it gets reflected about the y-axis, that's still going to be 0, 0. It's just going to be heading this way. So that doesn't change anything. But then you subtract 7 from it. So 1, 2, 3, 4, 5, 7. So that's going to be at the point 0, negative 7. Now let's take the point that was at 1, 1 on our original function. So if you plug in 1, 1, reflected about the y-axis, that's going to be over here at negative 1, 1. And then shifted 7 units down. 1, 2, 3, 4, 5, 6, 7. That's going to be a negative 1, negative 6 right there. And finally, let's take the point 16, 2. Goes over here. We reflect that about the y-axis. That's going to be over here at negative 16, 2. And then shift it down 7. Well, 2 minus 7 is negative 5. That's going to be at 16, negative 5, about right there. So negative 16, negative 5. And then we'll grab that one. Like that. All right, now let's look at each of these, the domain and range. There's a corresponding color. I'll just abbreviate D and R here. So the domain of this one, all the x values start at 0, with a bracket from left to right, and it goes to the right forever to infinity. The range starts at 0 again. It's the lowest y value reaches, bottom top, and it goes up forever, very slowly, but up forever to infinity. Now let's look at g of x, our domain for g of x. Notice it doesn't go left forever. The lowest x value reaches to the left is 3. So it'll be 3, and it includes that with a bracket. Keeps on going right forever, though, to infinity. And the range doesn't go down to a negative infinity in the y values, but the lowest y value reaches is 0. With a bracket, it does go up forever, even though very slowly, to infinity. Now let's look at the h of x graph. So the domain, this one, all the x values, this one also does not go left forever. The lowest y value starts out at 0. And goes right forever to infinity. But then the range, a little bit different here. Look at the way this one got curved when it got flipped across the x-axis. And now this one actually very slowly keeps getting lower and lower, so it does go down forever. So the range actually starts at negative infinity, but it doesn't go up forever. It stops right there at 6, including that point, so to positive 6 with a bracket. And the last one here, the domain, the x values, it goes left forever, so it starts at negative infinity. But it does not go right forever. The highest x value reaches right there, it is at 0, with a bracket included. And finally, the range on j of x. But it does not go down forever. The lowest y value reaches is right here at negative 7, included, so with a bracket. And then it does go up forever, very slowly, but it goes up forever, so that goes to positive 50. And that concludes the notes for AP Calculus on the topic of graphing and transformations.